delighted to have the opportunity to demonstrate RexP1, my ROS2 based Droid, at Breaking Breadboards recently. Breaking Breadboards is a community of makers and builders and enthusiasts like me here in Brighton, UK. It was great to test out RexP1 live and talk through some of the successes of the projects and plenty of the failures of the projects as well. Perhaps using Flux PCB Design, this video sponsor, with its AI CoPilot would have avoided some of those mistakes. Hi, I'm John, your concierge to the world of the Raspberry Pi Pico, Pico 2, robotics, IoT and other fun tech. Please remember to subscribe and join the community. This is a slightly different video, I guess, as I'm going to share an edited version of the live presentation from the night. I hope you enjoy it. If you like this video and it helps your learning or your projects, then why not drop me a cash tip using the super thanks button below the video, or alternatively there's a payment link in the description. Remember, I'm saving these up to get myself to the open source conference in San Francisco, and I'd appreciate your help in getting me there, and I'd love to meet you all there too. Thank you very much and enjoy the video. This video is sponsored by Flux AI, PCB designing software with AI built in. PCB design is just one of so many skills we need as makers. So it would be great to have some AI to help. Flux CoPilot is a built-in AI assistant to help you design your PCB, to place and modify components and connect them intelligently. With AI Auto Router to route your PCB like an expert engineer rather than a binary algorithm. Flux runs in a browser, so you can use it anywhere you have an internet connection and collaborate in real time with others on your design. Use the link in the description to go try out Flux AI today. Which will be the important thing to do. And the other thing I'm going to do is turn on the robot. Thank you. Now, obviously, we pray that the gods of demos are with me. Because as we know, things do not always work quite to plan. So we'll let that start up for a second. Look, things are turning, it must be all right. So, joke starter, coming from the wonderful world of industrial automation, who make the droids in Star Wars and sell them to the Empire and to the Rebels. And these are the droids you're looking for. I got a better reception at this Sirius Cybernetics Corporation, with their plastic pals. So yes, yeah. More seriously, this is my droid journey, and this is RexP1. He is basically a Raspberry Pi, some RP2040 zero boards, and the robot operating system, which I couldn't do it without, and a framework called MicroROS that builds off of that into the world of MicroROSy world. Oh, the gods of demo are not going to be happy to me, because that's joined and it's not doing anything. Okay. We might do a reboot and see if we can start up again. But or I'll give him a few more seconds because he takes a little while. The Python script that actually runs him didn't want to start properly, so I ended up putting a 2-minute delay in after he's booted up and he's got all his Wi-Fi up. So trying to guess, have I been talking for long enough, or is the adrenaline in my head such that he actually hasn't really started up his proper software yet? No, it doesn't. Yeah, okay. Never mind. I've got lots of video, and I'll give him another push towards the end as well. So what I was going to try and talk about is a bit about my journey to build this thing, which has been since Christmas, to be honest. when I really started and decided that I was going to build this. So I'll talk a bit about the mechanical design because that's important. And to be honest, that's where I'm making more mistakes than anything else. The control systems that actually make this thing move, honestly, it does move, and it has run around the hall and stuff. So, and the software control systems and how all of that works, and the whole software architecture that sits under this. So before I get too far into that, a bit of intro into me. So most of you know who I am. I'm Jon Durrant. By background, I'm an IT architect or an enterprise architect, or ran architecture team in various corporations. For the last 3 years, I've left all that world behind and got into the world of being a YouTuber and being sexy instead. And a Udemy trainer, and occasionally doing consulting to help companies and help do and build stuff and get things to work. Generally, that is more me getting in and getting out, rather than spending too much time actually working for them, because I want to spend most of my time building things like this. So, but it helps to pay the bills occasionally. So I have a YouTube channel. Please do subscribe, please do follow. More people who follow, the better. More people watch stuff, the better. YouTube like me that way. Yeah, so that's who I am. And this, of course, is RexP1. So it's, of course, inspired by my love of Star Wars. Absolutely. And he's an R series, i.e. he's based on this sort of 3-wheeled model design concept. He's not really a version R1 to R9. He's nothing of that. So I went with him being an E. He's, you know, E. We use it as the acceleration constant sometimes. So E seems like a good thing to do. X, because it looks cool. P, because he's got lots of Raspberry Pi technology within him. And this is version 1. Will there be a version 2? Probably not, because I can't imagine he's ever going to get finished. You know, there's always more that you can do and tinker with, isn't there? So he's not my first robot project. And in fact, I started my journey into robotics quite a while ago in completely the wrong place, because I started working on legged robots and with hexapods. And so the top left there, Hexy was my first journey into the world of robotics. And that was a really interesting robot. It was quite a frustrating robot, because it uses very cheap servos that are plastic, that are really easy to kill. And also it uses, of course, a lot of them. And it didn't really actually ever manage to generate enough volts to actually manage to power all the servos at the same time. So it tends to collapse a lot when it stands up, which is kind of frustrating when you're trying to teach him to walk. The one in the middle there, which is a high wonder kit, uses bus servos and uses LiPo cells and is a lot more stable. I didn't like their software, so I completely rewrote that and wrote it using ROS version 1 operating system. And we'll talk more about ROS in a bit. Going down to the bottom left, there is a little camera. There's a pan and tilt camera based on a Raspberry Pi. That was fun to build as well. And then I did a really much better version of that, really, which is the Robot Santa's head, which uses actually Raspberry Pi Picos and Raspberry Pis all at the same time, and also starts running some AI models to do face recognition and face detection. So he's able to actually wander around and actually look at you and see people around. So he's fun. There's robot arm. And then in the center there is DDD, my DIY dev droid. Yes, that is a breadboard on the back of some wheels and motors. And a lot of what I've got actually in RexP1 is, to be honest, based on DDD. And I've got about a dozen videos on YouTube talking through all of my journey and excitement And I'll refer a little bit to him because there are some bits that I learned from building that and playing with that actually have really helped make this successful and me not going down real stupid rat holes. But yeah, so now all I've done so far is introduce him. Let's talk about the mechanical design and how I built him and a few of the mechanical failures. There have been many. Let's talk about a few of the amusing ones. So R2-D2. I started at Christmas thinking I'll build an R2-D2 like model. I found some designs for R2-D2 online because there are some wonderful groups out there that do build replica droids that actually look like the things out of Star Wars. Not what I was trying to do, but you know, you can look at their plans, see sizes, etc. Now, R2-D2 is 1.2 meters tall, 0.6 meters wide, and is big enough that there is no way I could drive him around my flat. And also, I think my husband would divorce me. So I needed to think about slightly scaling this down. So RexP1 is about 50%, or it started out being 50%. So I aimed for him being 0.6 meters tall and 0.3 meters wide. Now he's actually 65 or 0.65 meters tall, so it's a little bit higher than I aimed for one reason or another, and he's just a touch bigger than 0.3 across, mainly due to the 2020 extrusion and me not wanting to cut it, because cutting it's hard work, certainly with a hacksaw. Yeah, so he's a little bit bigger than I intended, but he's pretty much to the scale. So when I started this at Christmas, my first thing was really to create a mock-up of this in Blender, and I'll talk a bit more about Blender. But yeah, I wanted a mock-up because I had some wheels. I knew how big motors were that I'd be using, and my first questions was, well, if you put wheels that big on him, on something that was half size R2 unit, would it look completely stupid, or would it actually look okay? So it's really good, and actually I was able, you know, within a couple of hours to have a nice little model, push it around, see what the wheels would actually look like on him, see how the motors would actually fit, would the housings get in the way, where are they going to have to think about things. So that worked really well as the real starting concept. And then I sort of continued with Blender. Now, other 3D design software for 3D printing and design do exist. You know, Fusion 360, Onshape, SolidWorks. I'm sure there are others. They all come with quite a large budget requirement, more than I could afford from my YouTube fees. Blender is amazingly free. Blender also has the slight problem, though, on the other hand, that learning Blender is something a little bit more difficult than climbing Everest. Made really because in Blender, everything you can do 20 different ways with 20 different near versions of what will come out at the end, and which is right for you. It's hard to tell. So Blender's quite hard to learn, but it does fit into other things. So as a YouTuber, I also have to occasionally make little graphics for YouTube, and you've seen one earlier, that my company logo. Actually, I can use exactly the same skills that I'm using to design him to actually do things in Blender for video purposes. So actually, there's nice overlap in skills there, which is quite useful. Yes, you know, there potentially is faster software for designing things in 3 dimensions. There is one other thing that I do like about Blender, and this is commercial. There is a extremely expensive, highly accurate gear model available for about $12, which means that I can print gears to allow me to turn the dome round, to tilt him, to do other potential things. So I can design nice accurate gears, get them to fit onto servos, get them to fit onto motors, etc. So that is quite nice actually in Blender. So I had some design principles as I set out, were on this extremely intriguing journey. So I knew I was going to make lots of mistakes. So I wanted everything to be as modular as possible so that I could build it in isolation. And when it went horribly wrong, I could rebuild it without having to reprint the entire thing. So everything as far as possible is a module at a time and as separate as possible. So on the screen at the moment, we have 3 modules, pretty much. We've got the motor housing, which is, we've got a PCB holder for holding the actual controller board, and we've got the ankle. And so all of those are separate parts, all of those are bolted together, and I can replace any of them. And in fact, I will be, because the ankle is not working out quite as I'd like. They occasionally get let go and drop off the legs, which is not what you want to do when you pick him up. One of the reasons they drop off is because they're connected to 2020 aluminium extrusion. This stuff I've already talked about here. So one of the things I realized very early onto this robot was that there isn't really a chassis connecting the 3 wheels together on the ground. In fact, the only place that all the 3 wheels actually connect together is at the shoulder, which is an awful long way away. And if I was going to do that in 3D printing, it's going to be really tricky. So I needed something that had a little bit of structural strength. And my solution was 2020 extrusion, which I think is really Meccano for grown-ups. And it has been great, though I've again made a few mistakes. We'll come back to one of those in a moment, but it's what gives it. So each of the 3 legs is 2020 extrusion, and the bar across the top of there for his shoulders is also 2020 extrusion. So that's what holds him together, and everything else then just comes out from that. And then everything else pretty much is 3D printed. Now, a lot of that is PLA. PLA is, for those of you who are not into the world of 3D printing yet, PLA is great. It's cheap, it's really quick to print, but it's extremely brittle, and it also is very heat sensitive. So I printed initially the motor housings in PLA. Not only did I crack several of them, but when I avoided cracking it, the warming up of the motor caused it to warp. So the motor housings and actually structural parts of him are printed in PETG. PETG on my printer is about 6 times slower to print, but it is actually quite strong structurally, and yeah, it survives the heating of motors and things. So yes, 3D printing on my Dremel printer that really needs replacing. So I said failures. Some things went wrong. So my initial version of those shoulders was to actually print PETG shoulder joints to actually have the angle between the front leg and the back leg. And this worked really well. You see, it can drive forwards and it can drive backwards. All good. It's fine. Now, when he turns around a corner, you've got a really powerful motor sitting on the end of a really long lever. And one motor going one way and one motor going the other way. So those back legs should really be straight in line, and they're now about 15 centimeters apart. Oh, so he now has steel braces on the back shoulders to hold them together, and it's the front leg that's forked off in a better structural way. The body, now when I've looked at this on the Droid makers groups and stuff, their robots are always fixed in drive position, or they have some that are just standing there with two wheels that's standing upright. They don't have any that actually morph between the two positions that R2 actually has, because R2 can actually morph and pull his center wheel back into his body and become a fully two-wheeled upright robot. Now that would be really difficult to do, but I thought, hey, I could actually make his body rotate. So I designed a cog system, placed his shoulders on bearings, and have a servo in there to drive that. And the first version of that, I had nice little tiny teeth on it, so that it would be nice and accurate and really, really smooth as it moved. Not thinking that actually little teeth means that it's actually not very far to actually use a little bit of force to push the teeth apart and cause it to constantly slip. So version 1 constantly slipped. Version 2, I printed bigger teeth. That worked really well until I put a little bit more weight on the body. And then that died. Version 3, which he's got at the moment, actually has two bearings braced together, holding that servo right in place. And that works really, really well, and was able to tip his body between two positions up until this morning, when I exhibited another wonderful behavior called center of gravity. Now, if I was going to demonstrate him today, he's set on Padawan mode, i.e. he drives at 25% of his speed capacity. Because if you drive him at full power, he quite happily toggles over backwards instantly. And yeah, the servo really didn't like being smacked very hard as he went over. And so the servo now rotates beautifully without any power. And when you actually control the servo, there's a lovely buzzing noise, but no movement. So yeah, so I do need to sort out his center of gravity a little bit. The reason his center of gravity is wrong is because I was really worried about that footprint of how big he is. And so I made the front wheel only 23 degrees off of the back. Now, I should really be about 30. And I decided to take the risk and that this would be stable enough. I was wrong. So what looks stable on, you know, in a CAD software is not the same as when you've got a fully loaded robot in front of you. That's okay. I can do that. I can take him apart and put him back together again. He is, yeah, built of plastic, and you know these parts are all interlinkable, and you know I have thought of other alternative names for him. You know, Mr. Rusty, because he is full of bolts, or alternatively Jenga, because it's quite interesting to see how many panels you can take off before he actually falls to pieces into a pile of bits on your desk. And the answer is an awful lot of parts you can take off. I've had most of, you know, the parts that, you know, out in order to get in and out without him actually falling apart, which is quite fun and exciting. So control systems, I guess we ought to talk about next. And I could talk about this all night. So we should talk about his architecture, because I've done something on this robot I've not done on any of my previous ones. So that's the exciting bit for me about the architecture on this. Talk a bit about how we get him to drive and what makes him actually move. Oh, hello. Oh, look. And because he's woken up, his dome will now work for a bit. So I might find a volunteer to distract you all from listening to me as we talk about him. So he can drive, and yes, that dome works. So he will go to sleep if no one's playing with him for a bit. It's a very simple Python script, but he will move. So I talked about my principles earlier. I've got another principle that I want to add to this as we talk about the control systems and that stuff, and that's reducing the number of connections. Because I've learned from lots of projects that connections are what kills your projects. The more wires and cables you have running between stuff, the more opportunity there is for things to go horribly wrong. And yes, that can go horribly wrong. So I wanted to, as far as possible, reduce the number of connections. And the way I'm going to do that is change from things I've done on previous projects, or I've seen most other people do, where you have this central brain and lots of cables going out to all of the LEDs, the sensors, all of the motors, and all of the controls. So instead of doing that, I'm actually going to put little brains, little microcontrollers next to groups of sensors in logical sequences, and then have them all talk back to the central brain. And so it becomes this distributed system where all of these parts actually come together and work together for the goal of the whole. And that, to me, as a software architect, makes much more sense. Hardware engineers may disagree, and I'm sure some of them will tell me about it later. But of course, everything's going to need power, and generally, most of the, particularly all of the motors and stuff, they're all on 12 volts running around this, and all of the electronics is generally got 5 volts running to it, though that 5 volts is actually running over a USB cable, which is actually providing all of the comms. So that's the architecture and how it all works. So if we look at even a single wheel, one of the back wheels there, they have 12 volts going to them. They have a USB cable telling that wheel what to do, and that's all that runs down there. Everything else down there is controlled on its own. Of course, it's got to have motors down there to actually make it move. And I chose to go with some highly geared motors. They're 131:1 gear ratio with a top speed of about 83 revolutions per minute. Now, the reason I picked them is because I've learned from DDD. So when I built DDD, I thought, oh, look, there's a kit on eBay that will give me some motors with some wheels on it. It's designed for a remote control truck to drive it around the park. It's really cool. And it's great. And if you power those motors up, they will drive at about 15 to 20 miles an hour, which is really great for going around the park and really shit for going around my bedroom or the living room. I will get that divorce again. So 83 revolutions per minute gives you a little bit faster than walking pace at full speed. Sorry, no, they're DC motors. They're DC motors, and I've got encoders on the back of the motors in order to know their position and how they're rotating. Actually, by being 131:1 ratio, you actually can drive these motors to quite amazing accuracy. So in one of my tests, I was actually spinning them to a third revolution at a time, and basically just stopping them. So absolutely precisionally on the same position every time around. It's amazing what you can do just by having all the signals coming back from the encoders and getting positions. Those gears also make it really quite strong. These are 45 kilograms per centimeter of torque, so plenty of grunt to pull the shoulders apart, which is really cool. But yeah, I mean, he is actually starting to get heavy, so they do need a good bit of power on them. The motors themselves are being driven by L298N dual H-bridge. So there's one of those sitting on each of the two wheels, so it's only using one half of that to actually drive the motors. And then there is a RP2040 Zero board, which cleverly I made to be exactly the same form factor, to make it easy to fit them. Now, you might realize at this point, or some of you who are a little bit smarter might realize at this point, I've broken one of my principles at this point, because those two boards need to be connected together. There are 7 wires going between those two boards to make that work. Yeah, this at some point I really need to redesign this. This is not a great idea. Those should be one board and all of the controls. The reason there's 7 is the motor connections themselves come off of the board on the right for you. Left, as I'm thinking about it, sitting next to it. The other left. Now, there obviously is more than just the motors on that board, so there are a few other things on there. So the other side of the H-bridge I'm using to potentially drive to headlights, so drive a headlight and a tail light if you like. That will be 12-volt LEDs, so nice and bright. There's some WS2812B LEDs because I want to actually put some nice strings of LEDs up the legs at some point and, really pimp him up a bit. I mean, especially it's Pride Month, he really needs proper full rainbow, I feel. So that needs to come. He's got I2C connections on there as well. I sort of got talked into that because I was talking about the final component on there, the HCSRI4s, which are ultrasound distance sensors or range sensors. And someone who I was talking to online really was trying to persuade me that you could make them really, really accurate by getting a really accurate temperature for the air, and therefore the speed of sound through air being very closely connected to temperature. I'm not sure that this is a place I really need to worry about too much, but anyway, I've got I2C there if I need them. So yeah. So the reason why he's got range sensors on those boards is because of something that's going to come next. So the idea is that this is not going to be a remote control car that Nicola is going to drive around the floor all the time, because that's kind of dull. So I do want him to actually be able to map his environment and to actually navigate. And so to do that, we need a LiDAR scanner. Where do you put a LiDAR scanner on this sort of shell? Because generally on these robots, you put them on the center of the head. The center of the head is at a strange angle and is not really a very great place for placing them. So the best place to put him, I can see, is to be on the front foot. Now, if you put it on the front foot, that means that there is this massive dark place of shadow that you can't see behind him. So we will then have a robot that can never go backwards because it never knows whether it's safe to do so. Well, the way around that is, of course, to put some ultrasound distance sensors behind him, like that, and then we can actually at least see behind. Actually, I will probably put some range sensors on the front as well, because I've also found from experiments with LiDAR with other robots that LiDAR is really, really good when you're pointing it at white surfaces. If you ever have black surfaces, like, I don't know, my piano, as it goes past it can't see a thing and has no idea. So actually being able to have some different sensing technology is quite useful. So then you can actually enrich the map as it builds it up. So that's the idea. Of course, ultrasound range sensors aren't enough to give you mapping, so you do need LiDAR, but they can at least tell you you are safe to move forward or you are safe to move backwards. So how about the dome then? So we have to be able to rotate the dome. Give it a little push. So yeah, there we go. Dome rotates. So it needs to be after that, and we need to be able to rotate the body. Oh dear. And we need to talk a bit about connections. So let's chat a little bit about the dome. So the dome is obviously is on a 300mm diameter cylinder. So I did look at what it would be like to buy an engineered bearing that could actually hold that. I think they were about 250 to 300 quid to buy a bearing for that. I decided that a Lazy Susan bearing would be a much better investment, as they cost about 10 quid. So he's got a Lazy Susan bearing in there with a 3D printed gear on top of that. And then that's being driven by a 24 BYJ48 stepper motor. Now, those stepper motors are not terribly strong, but they do become quite a lot stronger if you hack them and stop them being 4-phase and make them into 2-phase. So instead of having 4 coils, they only have 2 coils. The other advantage to that is that makes them much easier to drive with DRV, or much more possible to drive with a DRV 8825 driver board, which is much easier to drive than the sort of complicated logic that you need to do for the what the drivers for that generally come from the UN2003s. Yes, I've forgotten what they are. Is some sort of transistor things. But the problem with them is you've got to put lots of logic into your code to keep driving each of the different codes through. Whereas actually, if you're using a DRV 8825, you can just put a PWM signal through and tell it to just pulse at this speed, and great, and it keeps rotating. It's brilliant. It's much easier. So that's what I'm sort of doing. Hacking those stepper motors is really easy because it's just cut the red wire in the middle and cut the track between the 2 terminals that the red wire was going to, and then the 2 coils are separated. And yeah, there's some great stuff online about how much stronger the stepper motor comes. Now, anyone who knows a little bit about DRV 8825s and the steppers will know that, well, actually those stepper motors are 5 volts and that driver needs at least 8.4. And in fact, I'm driving 12 volts through that, but that's okay. It's a current controlled stepper. You're a controller, you can actually set it down to a current that is not going to burn out the coils. So the coils are not getting too warm, it's fine. It all works absolutely perfectly. And it's a great solution for driving the dome. The tilt mechanism. Well, I tell this morning that was going so well. I built the tilt mechanism based on servos, and I've used bus servos, and I've used Highwonder LX16As. The reason I've used bus servos is because traditional servos, you give them a pulse width modulation level and they move to that angle as fast as they possibly can, which is not what you really want the body to try and do. You want it to slowly move to its new position. And bus servos, you can tell, please go to this angle over this number of seconds. And that's what I was doing. So these two servos, I'm telling them both to move at the same time, but I'm telling one of them to take a little bit longer to get to its target position. And you can see that though they're both getting messages together. The other thing about those servers that is not so good is that they need generally driver boards. And that means more connections. And I didn't really want to do that. But then I did some more research and I did some experiments and I looked and I found that actually the driver board isn't doing anything very clever, and I think that a microcontroller can't do on its own. So I found with some level shifter, a diode, and a little bit of code, I can quite happily create half duplex UART and put it down the single pin. And that's all I need to do to actually drive those. And it works perfectly. So yeah, that's really, really a saving. And saves me about buying any more driver boards ever. So that is the mechanism from the shoulder for rotating. And you see it's got two bearings here, either side. Got our servo nicely strapped in there. And it's, yeah, absolutely turning that bit of 2020 extrusion around perfectly. Now, obviously, you know, it's not got the whole weight of the body, which I possibly didn't calculate, nor has it fallen over and smashed that servo several times, all of which may make this less weight. I need to think of a better solution for making it rotate. This isn't going to work, but anyway, never mind. So it does rotate. Here we have a demo of it rotating without a head. And that's on version 3 of the rotation mechanism. This is version 2 of the rotation mechanism. And that worked okay, as long as it didn't have the rest of the body as weight on it. So, you know, it's, yeah, it gets there. So finally, on my journey, software. And software is important because without software, he's not going to do a great deal. And there's two sides to the software. There is the central software running ROS2 that runs on the Raspberry Pi 5 that's sitting in the middle of him. And that's at the moment running some Python code. It probably will get migrated to C++ code at some point. Python's great, and I really love Python. And for prototyping this stuff, it's really, really quick and really helpful. But for robotics and signal processing for robotics, and it's got an awful lot of messages and data being thrown at it very quickly. And it just isn't really quick enough. So moving to proper languages is necessary, I'm afraid. On the microcontroller side, the RP2040 Zeros, and which it's running microROS, and that's all in C and C++. And I use a framework called FreeRTOS kernel. So that's RTOS is a real-time operating system. Basically, I need multiple processors running on there because some of them are dealing with comms coming in and out. Some of them are checking comms going out to servers. Some of them are, you know, calculating positions, etc. So to be able to actually split that up, I actually use an RTOS. And it works very well. Courses are available on FreeRTOS kernel by Dr. Jon EA on Udemy if you're interested. But really the hero for most of the software is the robot operating system. Robot operating system is currently in version 2. I'll tell you about that feature in a bit. That is a software feature. Or a maths feature. Version 2, they release a new release of this, not major 2 release, but every couple of years. So we're currently on a release called Jazzy Gillespie. They're all based on turtles because it's sort of their hero is the turtle robot. ROS2 gives you a whole load of tools to be able to build these environments and to actually control this, to look at what's going on the robot and to have visibility of everything. And a build system that will allow you to bind this and bind components of your model into just about every language. So I talked about doing things in Python and C++. I can run both of them together. I can write some components in C++ and some in Python and run it. I could have some in Rust, some in Java, whatever I wanted. It's, yeah, it gives you that flexibility, which is great. And that flexibility then comes into the libraries that are there. So there are libraries for the navigation and mapping, and all of those sorts of high-level capabilities that the maths is really beyond mere mortals like me to work on. And all of those algorithms all in that framework, which is really, really cool. So ROS really works by the concept of nodes. So each of my RP2040 boards is actually a node in itself. And the Raspberry Pi 5 is running one piece of software acting as a single node itself as well. And then those nodes then are able to communicate via topics, publishing messages on those topics and listening to the message on the topics. By doing services, a service in ROS2 terms is where you ask, you make a request because you want a response back and you want to listen. So it's that sort of synchronous request. And an action is a long-running request. Now, to be honest, I don't actually use services or actions. I've not used them on any of my robots yet. I've not needed to. PubSub works perfectly for nearly everything I actually do. Yeah, that's how he works. So on the Raspberry Pi there, I can actually type in some commands to actually look at the topic and look at all of the messages coming across that topic and see all the values as they're going across. You can also hand publish to it and things. And in a sense, that's exactly what Nickel is doing when he operates that. He's actually generating some messages and getting them read back. On the MicroROS side, MicroROS basically, I largely am using it as messaging framework for giving me reliable messaging transport into the ROS world. You can get those messages into, well, MicroROS runs on lots of microcontrollers, and on all of those, you can do those messages over USB, over UART, or on UDP. Now, I'm only playing on USB in this robot, and it's the easiest one to get running. So I've done this on a number of robots. So that robot on the left-hand side there is called a video turntable. It's a robot. It's got a single joint. And I wrote it as a single jointed robot. Obviously, robot center in the middle there has got two joints. It's pan and tilt. And there was a few more joints on, well, I suppose two joints as well on DDD. All of those robots are based on the concept of a central Raspberry Pi providing the brain, and then I'm using RP2040s or Raspberry Pi Picos in order to actually run the electronics from it. And then so ROS2 running on the Pi and MicroROS on the Pico. Now, you already know, because we've already talked about the controls, systems and design, that this robot is different because we haven't got a single RP2040. We've got lots of RP2040s. In fact, at the moment, he's got 3 in there. I reckon I'm going to have 7 or 8, at least, possibly 10, possibly 12. Every time I add something, I just will plug it in as an additional board or additional USB connection, and off we go. And they will all talk back. In fact, I'm going to make him a little bit worse than that, because I'm going to give him a second Raspberry Pi 5 as well. And I'm going to do that for 2 reasons. One, I want to run a couple of cameras in the dome, and image processing on Raspberry Pi 5s is quite an intensive So it's not going to be able to run the rest of the navigation stack at the same time. So I'm going to use a single dedicated Raspberry Pi 5 for doing the video and place it in the head. It's going to need to talk to the rest of the ROS ecosystem. Now, I could run lots of cables down and worry about not tying them in knots, but the head, the phone at the moment does 360s, so you know that's kind of difficult. I could put it through slip rings, but slip rings are kind of noisy for comms. So my intention is to run power over a slip ring and actually do Wi-Fi, which will be much easier. I mean, he's already got a Wi-Fi access point in the bottom anyway, because that gives me ability to get onto him nice and easily if he's out and about. So it's not going to be much of a problem to put Wi-Fi across to the top. But yeah, so how does all this control system work? Well, it's quite an onion, to be honest. And this is the onion just to get him to do what he's doing at the moment. Add to that onion the ability to do mapping, navigation, face detection, face recognition, other clever behaviors. It's quite a lot of software stack to get working on, really, I think. So, you know, at the center of that stack is the ability to make him move and make those motors go. And that's just pulse width modulation, you know, a duty cycle going out onto the motor controller board to actually drive the motors. That's really easy. Then need to read back speed. Now, we talked about there being encoders there, so I can read back the data coming from those encoders to tell how that motor actually is rotating, and that's the motor rotating before it gets into the gearbox, which then gives you really accurate positioning of that motor itself. Then we need cruise control, because when we tell him to move at a certain speed, it will be great if he moves the same speed uphill as downhill. And that means he's got to actually have some read back of what that speed is. And that's important to make him viable for moving around on his own in an environment. And we do that using an algorithm called proportional integral derivative, which is PID, which is a really standard algorithm. It basically is the same as coping with kangaroo petrol that we all had when we were learning to drive. It's actually, you know, predicting how the motor is going to respond and not over accelerating and then pulling back on it suddenly. So actually to get a nice smooth acceleration. And that's what the PID algorithm is trying to do. And each of those bits is just trying to modify a bit of the over prediction curve. So all of that bit so far that we've talked about is just sitting on the microcontrollers. The central computer and central Raspberry Pi doesn't want to worry about any of that. Doesn't need to. It's just all dealt for it. All it needs to worry about is then, you know, information that's starting to come out of those Raspberry Pi or RP2040s. So each of the motors actually then on controllers publishes their state. So they give information about what its current position is, what its current velocity is. There is massive ability to have effort in that. I'm not doing effort. I'm not sure I could calculate effort, so we're not doing effort. We are doing position and velocity. And it's taking instructions. It's taking a wonderful named message called the joint jog, which allows us to take the name of the joint we want to jog, and whether we want to go to a displacement, go to a particular radians position on, or we want to go to a particular velocity. And so we send that message, and that's what's making those wheels move. So when Nikhil pushes the button and makes him drive, that DualShock 4 is actually creating a message called a twist message. And twist message gives him linear and angular velocities. And we then need to convert those linear and angular velocities into joint jog messages in order to actually make the motors rotate. Yeah, which is what that slide says. So a twist message looks like that, really, linear and angular x, y, and z values. So if we put x as 1 in our linear, then that means go forward at 1 meter per second. Basically, if we put it as -1, it's backwards at 1 meter per second. If we could put 1 into a y there, that would mean going on this angle. He can't do that, nor is he very good at flying, which would be z. So we don't need to worry about that. We only need to worry about x. How about the angular? Well, x would be roll. Now, he's not very good at that, fortunately. He's actually quite stable in that direction, so he doesn't do that. Pitch, he's actually quite good at pitching, but I wish he wasn't. So we really shouldn't be doing pitch. That should be not. So the only one really should worry about is Z. So it needs to be able to rotate. And so those give us a rotation, and those are in radians per second. The other thing to think about with radians, which I need to think about a little bit, is where is he rotating around? And at the moment, he's rotating around the center of the virtual axis that would run across, or axle that would run between the back wheels. That isn't really where I'd like him to be rotating around. I'd rather he rotated around the center of the robot. But maths to do that's a little bit tricky. So he's not doing that right now. So maths, yeah. So we've got some calculations to do here. If we want him to go forward at 1 meter per second, then we need to instruct the wheels to rotate at a speed in radians per second. That's easy because actually it's just divided by the number of the radius. If we want to get them to go rotate and to turn, then we actually need to worry about actually what the dimensions of the wheels are and their positions in order to calculate how you get from the speed, meters per second and radians per second into actual revolutions per second of radians per second of the two wheels. Now, we saw him misbehaving on a rotate a little while ago. Now, that's because there's a tan in this algorithm, and tan tends towards infinity, which is kind of awkward because if it tends towards infinity, that means that the speed of those motors tends towards infinity, which tends to mean that he accelerates around corners, which is not a great trend. So he is limited, and I thought he was limited perfectly, but obviously there is a case I have missed. But yeah, I have to limit those in proportion, otherwise he would only go straight between the speed of the two. And basically, I'm limiting him by the proportion of what would be his forward velocity. It's not perfect algorithm, and as you've seen, so but yeah, the things that you have to think about when you suddenly find that you've got tan in the middle of your algorithm. You know, the things I didn't learn when I was at school learning about trig. But so yes, so this is RexP1. It is, you know, designed in Blender. He's built as 2020 extrusion and a lot of hours of 3D printing and a lot of bolts. The time I am ordering so many bolts from Amazon, it's ridiculous. and a lot of iterations. His control system, I quite like this whole concept of being distributed and using these small components to actually run stuff is really working really quite well and is extensibly nicely. So, you know, before Evolve 25, I intend placing a nice little screen in that central hole on the dome, and that will just be a WaveShare RP2350 touch screen, where I'll put some code on there and it will listen to ROS messages and behave accordingly, and it will just fit into the rest of the architecture. And I've talked about stepper motor control, and I've talked about braking bus servos. I've talked about the operating system and the whole software, to which is really all about simple ROS2 at the moment. There isn't actually anything particularly complicated he's doing. It's really all pub/sub architecture, which is, as a maths and some fairly GCSE level maths, actually. It's not actually, we haven't actually got into the complicated maths. That comes when you start getting into navigation. But yeah, so there you go. Demo. And there's more of him online on YouTube and me talking about various bits of him as we go. So yeah.
Awesome. Any questions?
Jon, that was great and great fun to see. I guess when you add all these extra units, there's going to be a great demand for additional power. And so presumably you'll have to put more and more batteries in it. And there's a sort of consideration here, I was thinking, is to scale down the size of the original one. Your batteries are going to go higher up, because you have a big fat base at the bottom to spread them on. So I suppose my question is, have you thought about the effects of scaling on central gravity of batteries weight?
Let me think about that.
Of course.
No.
Well, what do you think? I mean, what's power like at the moment?
I haven't run him long enough to actually tell. So to be tested. There is quite a bit of power saving stuff I can do. I mean, it's certainly, he's using 2 LiPo3 batteries at the moment. One is providing power for the Raspberry Pi 5, the RP2040s from a digital circuit point of view, and the Wi-Fi access point. The other one is powering all of the motors, and they are separate and deliberately separate. When I add an additional RP20 Raspberry Pi 5 into the dome, I will give that a separate battery on its own right. So because of that, there is a degree of scaling and a degree of separation, which is important, and it's sort of working okay. Those LiPo 3Ss are quite chunky. They have a really good amount of current capable in them. So I think it's probably going to be okay. I have got crazy ideas, like, could I take him to the Pride March and have him, could we march with him around with Silicon Brighton at Pride? And that would be great. Has he got enough battery to get around there? No way. So I would have to think of alternatives. I don't know. Could I make him a little bit more hot swappable with batteries to cover off that? Could I, for going around my house and becoming a security bot, could I make him actually have charge capability? There might be a switch of battery, because I mean, at the moment he doesn't really care as long as he's got 12 volts coming in and it's got a reasonable amount of amps in that power. It doesn't really care what the battery source is. So there are some better battery solutions that I possibly could move to, which might help me as well. Doesn't really answer the question around weight, which, I don't know. As long as the weight, part of the weight problem is so far is about rotation of the body. If I just say, actually, better engineers than me have thought about this from Droid building and have decided this is a really stupid idea, don't do it, and just fix it, then actually some of that problem goes away, and it probably doesn't matter, and those 45 kilograms per centimeter motors, 2 motors at 45, that's a reasonable amount of push. So is he actually going to grind to a halt and not be able to move around and go up hills? I don't think so. more a problem is could he topple over because the motors move, or the batteries move. So batteries need to be fixed. Things are not as fixed in the bottom as they could be right now. But no, there are always improvements. That's a very long answer.
How is the controller connected to the just through one?
So it's Bluetooth. So it's a DualShock 4 controller. So it's just, you know, like if I was playing PlayStation at home, it's just using Bluetooth to.
I didn't know separate.
Yes, you can. Yep. You can buy them separately there, and they. I have lots of them because I worked for PlayStation.
I don't think you can get it to rotate about the same time. I think with the wheel geometry you've got, just off the top of my head, I think you can only rotate around an axis which is along the line extension of the axis.
I think if you vary the speed of the, so if you're doing constant speed on the two motors, yes, that's absolutely true. If you are prepared to vary the speed of those motors as you go through the arc, then I think you can.
I don't think so, but I think you can go forward and then rotate and then go back. But
yeah,
just off the top of my head,
yeah.
I could be wrong.
You could be right. It's something.
I was just trying to think if the wheels weren't orthogonal to the axis, then they're essentially staggered. That would give you more possibilities. But obviously you want them to look nice like that.
Well, also I want it to be structurally strong, as we saw earlier. He's doing all right. I mean, he hasn't toppled over backwards at all when he's been drone.
Presumably that's the Raspberry Pi in the little white box there.
No, that's the Wi-Fi access point. Actually, the Raspberry Pi is just the other side of it. It's not in a nice white box. It's completely exposed with a USB hub on the back of it to provide a lot more USB ports than just the 4 that comes out of the back of the Raspberry Pi. Because I need to be, sometimes he goes wrong, and if I was demoing him in an event like this, and I wanted to get on to log on and see what was going on, then I need a way of doing that. And also, when I put devices in the dome, I want that to be connected by Wi-Fi rather than running cables and worrying about.
So it's essentially like a Wi-Fi route.
Yeah, that's what it is. It is literally a cheap travel Wi-Fi router.
Hi, a brilliant robot.
Thank you.
Just a matter of mechanical curiosity. Why didn't you use a triangle at the bottom?
To connect the 3 wheel.
To triangulate the 3 legs.
Because R2 doesn't have one.
Okay.
R2D2 and other R series droids do not have that. And I was trying to be. I did an hour about this, and I decided to go with the risky and exciting route rather than the simple and guaranteed route.
Yes.
As you see, I've done that a few times on this project. That isn't necessarily a good thing, but hey, I learned a few things.
It's good.
Well, the future to do on your list would be to look at the software used in the segways to stabilize them, so that you could solve that problem that way, and then go down to 2 wheels. Well, no, you can keep the 3 just for historical purposes, but
I have thought about doing a 2-wheeled robot, and I may do a 2-wheel robot at some point. Though, actually, before that, I want to do a 4-wheel robot, but a 4-wheeled omnidirectional robot, not using omnidirectional wheels, but actually each wheel that can separately rotate itself, which I think have seen some really interesting robots designed online. And so, yes. So the rest of the 2020 extrusion is at home, connected up as a nice cube, ready for me to start work on that one, which I thought I'd be doing in, 6 or 7 months, not realizing that 6 months in, and I've still got probably another year's worth of work to do on this.
Did we have a question online? Perfect. So we have a question online from Dan that says, this is all fascinating and it's great to see it moving around. Is it going to be at Evolve 25 for people to drive?
It's going to be thank you, Dan. It's going to be at Evolve 25 for people to drive. Dan, you can drive it. I'm not sure I'm trusting anyone else, but you can drive it, Dan.
Hint, hint.
Dan will be at Evolve 25 too.
You're doing a swap. Is he going to have a robot for you to drive?
Well, I don't know. I mean, Dan makes this thing, who was here the other week. So yeah, so he will have his companion robot, or one version of it. I don't know. There are so many versions going on that. Yeah, he will have a version of that with us.
Hi, it was a great talk. The cutouts on the front, and then you've got some more cutouts on the dome. Have you got plans for that, or is that like just access ports? Or
yes. So R2 has lots and lots of tools and toys and things. So my plan is the design is really to allow me to place in panels with toys and fun things on it. The reason I left the panels off is so you can see inside.
Yeah.
For Evolve 25, from a health and safety point of view, I won't have any panels open. Yeah. So I will, over time, evolve cool and interesting things to put in them.
Brilliant.
Can you remind me what you said the bearing was used on that?
It's a lazy Susan. You know the food turntables. That's basically all it is.
Had you considered using a belt drive for the tilt?
No.
NMEA 11 stepper motor and then a splittable.
No, I hadn't. That's a possibility. That might be a good idea. I was toying after I broke it this morning with the idea of just sort of having a flexible belt with that at the bottom with just a stepper motor that pulls towards it, and just sort of pull yourself up. But not entirely.
On the other end.
not entirely strong, but but yeah, it is interesting because part of the problem here is I'm trying to move it at the center of axis, which is of course the weakest, or that requires the most amount of strength possible, whereas the actual weight of it is as far away from that as possible. So if I could actually work out a way of getting the mechanism to be at the base of the robot, and therefore a long way away from the point of the axis.
You could use a lead screw.
Yes.
Yes.
Yeah. But yeah, I could possibly use look at a lead screw mechanism. The other, of course, it's arcing, so you've got to have some sort of slip on the other end.
Just put a hinge on it.
What, in the middle of the screw?
Yeah, have to think about that.
Yeah, I was wondering whether you could just put a hinge on the end. I don't think you can. I don't think it's going to move like that. You might be able to hinge both ends, but you'd have to. It's going to have to rotate. Both ends are going to have to rotate in order that it continues through the arc. Alternatively, I could get a much bigger 3D printer and print myself a large cog bearing.
Yeah, you could.
But Creality Bamboo have just relaunching their H2D with 40-watt laser cutter module as well. I have been looking at it, though. Is $3,000 too much for a laser print for a 3D printer? But hey, it solved my problem.
Yeah, I mean, also a water cutter if you can afford it.
Well, yeah. To avoid I might need a workshop in order to avoid the divorce, which is also quite expensive. There's quite a few things that might be needed on this row. Jamie, you've got a workshop, haven't you?
It is very small.
Or he says several of us could go together on a workshop.
Oh, you have the price per square foot of property in Brighton, which is not cheap.
True. Yeah, workshop at the other side of the downs.
Cool. I just have a question, John, before we wrap it up. Have you considered, this might be a daft suggestion, so humor me. Have you considered external power for Pride? Like if you carried some kind of battery bank and kind of had a wire to it, or like
For me or for the robot?
Both. Is that a viable solution, or I know ideally it would all be on board, but for those longer events where because it would have to run for a significant amount of time for those events, and I think anyone who's seen Pride, the parade is stopping and starting, and it's kind of like for those one-off events. Do you think that could be a solution?
It could be. I mean, that's a possibility. I mean, yeah, and often groups have support vehicles that are driven behind them and stuff. We could point 50 car batteries in the back of the support vehicle and run a large cable. It'll be fine. What could possibly go wrong?
Trip hazard.
I think I'm not sure that external batteries really necessarily help. I think fast hot swapping would be the best option, really. I mean, to be clear, there is no way he's going to be ready for Pride 2025. He might make Pride 2026, but there's much too much that really needs fixing and sorting out. But next year, who knows? Could be fun if I get there. The other thing is weather. He's really not designed for wet weather. I haven't really thought about wet weather modification at all. So
you mean the hole on the top is not for his umbrella?
Well, I mean the hole at the top was for some clever little tool at some point. But yes, no, he really, he definitely is a dry weather only robot right now, and I think he would always be. So otherwise, we will be calling him Mr. Rusty at the least.
Yes, yeah. Amazing. I think that's it for questions then. So yeah, big round of applause for John. Thank you very much.
Thank you very much. RexP1's next big outing is going to be Evolve 25 on the 4th of July in Brighton. That's a rather different environment, and I have some work to do to make RexP1 fully enclosed and safe, along with removing the troublesome tilt mechanism for a bit anyway. If you like this video and it helps your learning or your projects, then why not drop me a cash tip using that super thanks button below the video, or alternatively there's a payment link in the description as well. I'm saving these up to get myself to the open source conference in San Francisco. That's a long way from here, and I'd appreciate your help in getting me there, and I'd love to meet you all there too. Thank you very much for watching. Please do like the video and please subscribe for more. Bye bye.